Okay, thanks, Martin. So, yeah, thanks very much for giving me the invitation to speak here, and thanks to all the organisers for all the outstanding work they've done in rather difficult circumstances. So I'm going to speak about two interesting invariants of a group which we call length and depth. So these invariants are defined in terms of the subgroup structure of the group, and they're designed to sort of, in some sense, measure the complexity of the group in terms of the subgroups of the group. Okay, so let me begin by discussing length. So length is quite a classical notion. It's been studied for several decades. So let's take G to be a finite group. So we'll work with finite groups mainly for the talk. Hopefully there'll be a little bit of time towards the end where I'll try and extend some of these notions to infinite groups and even other sorts of algebraic structures, but we'll stick mainly with groups. Okay, so G is a finite group, and then we'll have this idea of an unrefinable chain, or sometimes called a maximal chain. So this is just a sequence of subgroups from G down to the trivial subgroup, where at each step in the chain we drop down to a maximal subgroup at each step. That's an unrefinable chain. Okay, so this leads naturally to the definition of length. So the length is simply the maximal length of an unrefinable chain. So in the description above here, there's T inclusions, and we'd say that that was a chain of length T. Okay, so the length is the longest unrefinable chain. So it's a very natural thing to consider. So if you take the subgroup lattice of G, it's just the longest chain in the subgroup lattice of the group. So it's a very natural thing to look at. So just some immediate observations to get started, and some notation which I'll use for the remainder of the talk. So if we take a positive integer n, then we'll write omega n for the number of prime divisors of n, including multiplicities. Okay, and we'll set omega 1 to be 0. Okay, so the first observation is, of course, that since this is a strictly descending chain, at each step you're going down to a proper subgroup, so you're losing some prime divisors at each step. So, of course, the length of the group G can't be at most, sorry, is at most the number of prime divisors of the order of the group. And, of course, that's at most the base 2 logarithm of the order of G. And if you take G to be a 2 group, then these inequalities are both actually equality. Okay, so that's the first observation. The next observation would be if you take a soluble group and you consider a composition series for G, and, of course, all the composition factors are just cyclic groups of prime order. So in that situation, the length is as large as it could possibly be. It's actually equal to the number of prime divisors of the order of the group. Okay, it turns out that this condition here doesn't quite characterize soluble groups. There are insoluble groups that also have that property. I'll show you an example of that shortly. Okay, so that's the soluble case. Two nice properties of length are monotonicity and additivity. So the monotonic property is pretty obvious. If you have a subgroup, then the length of the subgroup is at most the length of the group. That's clear. And it's also not too difficult to see that if you take a normal subgroup, then length behaves nicely with respect to quotients. Okay, it's additive. So this additive property is particularly nice. So if you think about it, what it means is it means that the length of a group is equal to the sum of the lengths of its composition factors. So really, this reduces immediately the study of length of finite groups to the lengths of simple groups. And that's the case that's been investigated quite extensively. Okay, so that's the definition of length. Let me make a couple of connections to two different parts of mathematics where length arises naturally. And these two connections have motivated quite a bit of research in the last, say, 20, 30 years on length. So the first one relates to work of Babai in the 1980s. So he was interested in looking at algorithms for permutation groups and trying to study their computational complexity. And if you think about these problems, you're faced with the following situation where you have a permutation group of degree n, so some subgroup of Sn, and you might be interested to think about, well, how many generators do you need for G, and how is that related to n, the degree of the permutation group? So if you take a generating set of minimal size, so say it's got d elements, and you just fix some arbitrary ordering on those elements, then of course you can construct a strictly descending chain of subgroups from that just by throwing away one generator at each step. And this will be strictly descending because we started with a minimal generating set. Okay, so we have a chain of length, we have a strictly descending chain of length d, so this d is at most the length of the group, because that's the longest possible chain you could find in the subgroup lattice. And then by monotonicity, the length of G is at most the length of Sn. So if you want to get a bound on the minimal number of generators for G, then one way to do this is to think about the length of Sn. And this is what Babai was interested in. Okay, and I'll say more about the length of Sn shortly. In a different direction, Solomon and Tyrrell also got interested in length in a big way in the 1980s, and this was coming at things from a different sort of problem. So here the setup's as follows. So we've got a finite group H, which we write as a semi-direct product of G by A. Let's assume G and A have got co-prime order, and let's assume that the centralizer of A and G is trivial. So this just means that A is a group of fixed point free automorphisms of G. That's the situation we're looking at. So here you've got Thomson's famous theorem from 59, proving conjecture of Frobenius, that says that in this setup, if A's got prime order, so in other words, if G's got a fixed point free automorphism of prime order, that forces the group G to be nilpotent. Okay, so that's Thomson's theorem, but this can be generalized. So it turns out that with that setup, if you use the classification of finite simple groups, it's known that that group G has to be soluble. But of course, it doesn't necessarily have to be nilpotent in general. So you can ask, well, how far away from being nilpotent is that group G? So this can be measured by looking at the fitting height of the group. And the conjecture here, which is still open, is the fact that the fitting height of G is bounded above by the length of A. So that would be a nice, if that could be proved, then that would be a really nice extension and generalization of Thomson's theorem, because if you take A to have prime order, the length is 1, so the fitting height is 1, so the group is nilpotent, but this is a generalization of that. So this is one of the reasons why Solomon and Tyrrell got interested in looking at the lengths of finite groups, coming at it from this problem about automorphisms of soluble groups. So I think here the best known result in full generality, I think this has been proved under, if you add some extra conditions, but I think the best known result in full generality is that the fitting height is at most twice the length of A. So it's still an open problem. Okay, so that motivated some interest in length in the 1980s. We'll come to look at some examples shortly. Let me now just turn to depth and introduce the depth notion. Okay, so it's very sort of natural to consider this. So if length is the maximal length of an unrefinable chain, then why don't we consider the minimal length of an unrefinable chain? So length is sort of asking how slowly can you descend in an unrefinable way to the trivial subgroup, and depth is saying how fast can you do it, okay, in an unrefinable way. Okay, so we'll write lambda G for the depth of our group G. Okay, so some first observations. Well, of course, the depth is at most the length. And it turns out those two numbers can be equal. And there's a beautiful characterization of this due to Iwasawa from 1941, who proved that the length and the depth are equal precisely when the group is supersoluble. Okay, so this is the situation where you have a normal series with cyclic factors. Supersolubility is also characterized by the property that every maximal subgroup's got prime index. Okay, so that gives you a characterization of the situation where any two unrefinable chains have got the same length. That's what lambda G being equal to L of G means. So that's a nice situation. Depth is more complicated than length for many different reasons. It's in some sense more difficult to study because it doesn't satisfy some of the nice properties we observed for length. So it's not monotonic. So you can find subgroups which have larger depth than the group itself. And it's also not additive either. So there is a relationship. It's not too hard to see that there's a relationship between the depth of G and the depth of a quotient group, but it's not, you're not going to get an equal sign here in general. And here's just a little tiny example to illustrate that. So if you take this one-dimensional affine group over the field of 8 elements, so it's a group of order 56, you have this normal subgroup here, this elementary abelian 2 group of order 8 as a normal subgroup, and you have the C7 on top, and that's acting transitively on the non-identity elements in the normal subgroup. So the depth is actually 2 because the C7 is maximal. As soon as you add in one extra element from outside, then you get the whole thing. So the depth is 2, but the depth of the subgroup N is 3. It's an elementary abelian 2 group. The depth is 3, so the subgroup's got larger depth, and the depth of the quotient here is the C7, so it's depth 1. So you can sort of see that in both of these inequalities, they can be strict. Okay. So in some sense, this doesn't reduce, so the study of depth for finite groups is not automatically reduced to simple groups, but they'll be the family of groups that we've mainly focused our attention on. Okay, so I mentioned previously that one of the connections for looking at length comes from Babai's work on computational complexity. So let me go straight to looking at the length of Sn. So here's a beautiful theorem of Cameron, Solomon, and Tyrrell proved in the late 80s, which gives an exact formula for the length of Sn. Okay, here it is. So it's roughly 3n over 2 is the exact length. And it's remarkable, there's no exceptions to this. This is true for all n. So it's roughly 3n over 2, and then you have this little error term on the end, bn, which is the number of ones in the binary expansion of n. Okay, so a lovely result that gives you the precise formula for the length of Sn. And therefore, the length of the alternating group, of course, is just 1, subtract 1 from this expression. Here's an example. So the length of S6, so you plug 6 into that formula and you get 6 pops out. And then here's a chain, here's an unrefinable chain of length 6. And this sort of illustrates, this sort of shows you that it's not too hard to show that the length of Sn is at least as large as this number. Showing that the length is greater than or equal to something is not necessarily so difficult because you just have to exhibit. You have to show that such a chain exists. What's really hard is to show that you can't beat it. You've only got to consider all possible chains. And here you can sort of see where maybe the binary expansion comes in even at this point here. So we're writing 6 as 2 plus 2 squared, and you can sort of generalize this in a natural way. And then you just take these chain of subgroups, and this is a chain of length 6, and the theorem says that you can't beat that. Okay, so as I say, proving this is actually equality is quite tough. So let me just explain briefly how the argument goes, roughly speaking. So what you're interested in is you're interested in analyzing the first subgroup that you drop down to in an unrefinable chain. So of course it's a maximal subgroup of Sn, and we know lots of things about maximal subgroups. And the game is to show that the length of a maximal subgroup is at most this expression minus 1. And so the argument goes by induction. So you look at this maximal subgroup G. It's either intransitive, imprimative, or primitive. The intransitive and imprimative cases, you're either a direct product of smaller symmetric groups or a Reith product of smaller symmetric groups. They're handled by induction, straightforward. So you get down to the case where G is primitive, and then you need to do some work. So if you remember, the length is bounded above by the log of the order of G. So if it's going to be a counterexample to this bound, then the order has to be sort of sufficiently large. That's restrictive. You can use the Onan-Scott theorem to look at the possibilities for G for the primitive cases. You reduce it down to the almost simple case, and then you need to apply the classification of finite simple groups and some work on bounding the size of G in terms of the degree n. Okay, so that's sort of how the proof goes. It'd be interesting to know if it's possible to prove that result without having to apply the classification, but that seems rather difficult. Okay, so that's the length of Sn. So the thing to take away here is that there's an exact formula, which is very nice, and it's roughly 3n over 2. In particular, it tends to infinity with n. So the length of symmetric groups grows. Let's compare that with the depth of Sn. So if we now turn to depth, remember the depth is now how fast can we descend to the trivial subgroup. Well, the situation is remarkably different. This was one of the first results that we found, and it was sort of quite surprising to us. So the depth of the symmetric group is bounded by a constant. In fact, you can bound it by 24. Okay, that's for all n. We're not claiming this 24 is sharp. I don't know any examples where the depth is actually bigger than something like 9 or 10, but 24 is what pops out from our proof. And I'll explain the proof because it's got a really nice idea in it, which is quite a neat application of a very deep theorem in number theory. Okay, so for simplicity, let's just assume n's at least 12 and even. If those conditions aren't satisfied, there's a little bit of modification needed, but it's not too much. It's not too different. Okay, so the point is here. So what we observe is that if you look at n minus 3 is an odd integer. It's at least 9. So by the Ternary-Goldbach theorem now of Helfgott, you can write n minus 3 as a sum of 3 distinct primes. Okay, so that's what we use. So we use that result. So you can find primes p, q, and r. So you can write n as in this expression here. And the reason why we want to do that is because now we can focus attention on this subgroup H. So H is this direct product of symmetric groups, all of whose degree are a prime plus 1. So the first observation here was that we observed early on that the depth of a symmetric group of degree of prime plus 1 is very small. Okay, so that's why we were drawn to that. So we go down to this subgroup H. And although H is not maximal inside G, it's not far from being maximal. So it doesn't lie too deep in the subgroup lattice. Okay, then what do we do? So then we look at each factor in turn. And if we take, so if T is some arbitrary prime at least 5, and we stay away from 7, 11, and 23, where you have to just make a small modification, then you can define an unrefinable chain like this. So I'm going to stop the chain at K. but you drop down to the alternating group in the first step, and then inside the alternating group, you've got PSL2T acting on the projective line that embeds you inside the alternating group as a maximal subgroup. And then inside PSL2 over a prime field, you've got this subgroup K, which is maximal, and K is one of these little tiny alternating or symmetric groups. Okay, and those Ks have got very tiny depth. In fact, the depth is at most 3 for those subgroups. So that tells you that the depth of this symmetric group, ST plus 1, is at most 6. And so if you want to now get down from H to the trivial subgroup, you can certainly do it very crudely in 18 steps, because I would just drill into that first symmetric group and take that one down to the trivial subgroup, and then I'll do the same with the second, and I'll do it with the third. There's probably some maybe more efficient ways to do that, but that's a crude way to see that the depth of H is at most 18. Okay, and then the point is now, you've got to be a little careful if there's some coincidences amongst P, Q, and R, but you know, in general it's not a problem. Roughly speaking, this H is a second maximal subgroup of the symmetric group. You just drop down to this intransitive subgroup here, it'll be maximal. So you can get down to H in 2 steps, and then 18 more steps gets you down to the trivial subgroup, so you get depth at most 20. Okay, and the 24 comes from the fact that you've got to do a little bit of tweaking to get around some of the special cases. But 24 comes out. So I say, I think if you assume the Goldbach conjecture is true, then I think you can get depth at most 15. But probably the real value, the best possible, might be something like 9 or 10, but that seems hard. Okay, so that's the depth of Sn. What about groups of Lie type? So let me just state really what the main theorem here is, and this is due to Solomon and Tyrrell, motivated by their thinking about automorphisms of solvable groups. So here's a statement. So this was proved in a series of 2 or 3 long technical papers. It's really quite hard. This is quite a hard result. Okay, so the length. So you take a simple group of Lie type over FQ, take its twisted Lie rank to be R. So this is sort of what the twisted Lie rank means for PSL and PSU. Okay, and then what do they say? So the statement, the main result is for Q even. So if you assume Q's even, then they can actually get an exact formula for the length, which is, I think, sort of an amazing result. So if Q's even, then the length, apart from one very special case where you've got to add 1 to the number here, is the length of a Borel subgroup, so the length of the normalized of a Selov2 subgroup, plus this twisted Lie rank. Okay, remember the Borel subgroup here is a soluble group, so it's just given by the number of prime divisors of its order plus the rank. Okay, so again, a little bit like the symmetric group, it's not hard at all to see that this is a lower bound for the length, because you can take the Borel and then you have a sort of a nested sequence of parabolic subgroups taking you from the Borel up to G. That would have length R. So easy to see that this is at least that number. What's really hard is to show that it's actually equal to it, that there's no longer chain. Okay, so that's for Q even. For Q odd, the situation's more complicated, and there's no known formula in general for what the length is in Q odd in full generality. What they can show is that if what's interesting here is if you look at, it's really the exponent of the prime is the key thing here. So if Q is P to the K, P is an odd prime now, and you look at this K, then if K is sufficiently large, and sufficiently large will depend on the prime P, then in fact the conclusion is still true. But if K is not, if K is small, then in fact you can find longer chains in general than passing through the Borel and going through the chain of parabolic subgroups. Let me give you an example. So if you take PSL27, okay, so PSL27, its Borel subgroup is this little Frobenius subgroup here, C7, C3. So the length of the Borel plus the rank is 1. So the length of the Borel plus the rank is 3, but in fact you can find a chain of length 5. Okay, because you could pass down to S4, and then you can take that chain inside S4. So it's actually not optimal. So you can actually, there are exceptions for, this is where K would be 1 for the prime 7. Yeah.
Does this K also depend on R, say on the type of P?
I don't think so. I don't think it does, actually. I mean, I'm not sure if they have explicit bounds on what the sufficiently large actually means in terms of the rank. I think it's just actually given in terms of the prime P. Yeah, there's going to be, I think there'll be a situation like that, yeah. Yeah. Yeah, I must say I've not studied all the details of that, of the paper where they actually proved this for for odd primes p with it being sufficiently large, but it's a hard result. But this example here shows that the length of L27 is 5, and of course that is the number of prime divisors of 168. So that's one of these examples I mentioned before. So it's an insoluble group, but the length is as large as it can possibly be. Okay, length for groups of Lie type. Okay, what about depth? Let's turn back to depth. So here, I'll just start off with an example. So for alternating groups, the depth is at most 23 by our theorem. So you might ask, well, do all finite symbol groups have bounded depth? Well, no, they don't. So even just turning to PSL2, you can build groups of arbitrary large depth. So here's how you might do it. So if you take PSL2, p to the k, let's assume p is odd, and let's assume k is odd to keep things simple here, then just by inspecting the maximal subgroups of this group, you can show that the depth, we have a formula, it's the number of prime divisors of the exponent k plus the depth of the group over the prime field. And the depth of the group over the prime field is tiny. It's 2, 3, or 4 according to p. Okay, so in particular, if you take k to be the product of the first n odd prime integers, then the depth will be bigger than n. Okay, so you can find arbitrarily large depth for simple groups. Our most general result here shows that in some sense that this behavior is generic. So if you take a simple group of Lie type, any simple group of Lie type over field fp to the k, and if we assume p is odd, then we have a bound, and of course we're not claiming this is best possible at all, but we have a bound which is of the form a constant times omega k, which is sort of like this is actually the correct value here for PSL2. The 3 and the 36 clearly are not optimal, but that was about an explicit bound that we could get out. Again, for depth, it's not so hard to get an upper bound because you just need to exhibit a chain. Again, what's hard is to try and generate lower bounds on the depth. And in fact, we don't really have a good way to do that. So we don't really have I can't really put anything on the left-hand side here as a lower bound. It'd be nice if we could do, but that seems rather difficult in general, because you could have somewhere, you could have a simple group, and inside of there's some little tiny, irreducibly embedded simple group of rather small depth, and so you'd have to be able to detect when that happens and when it doesn't happen, and that seems a hard problem. Okay, but that was for p odd. When p is 2, basically the same bound does hold, but you've got to be careful in a handful of cases. I'll explain one of these in a bit more detail. So you've got to be careful in these cases here. So basically these two rank 1 groups and then these unitary groups, you've got to be a little bit careful. Okay, I'll say more about that in a second. Let me just explain sort of roughly how you prove that upper bound. The idea is really easy. So the idea is that we want to exploit the result about symmetric groups. Okay, so we know symmetric groups have got very small depth. So what we want to try and do is we want to try and find a symmetric group inside our group G without having to go too far down into the subgroup lattice. Once we can land on a symmetric group, then we can apply our result that its depth is bounded by 24. So here's how we might do it, say, for this family of symplectic groups over the field of size 2 to the k. And let's just, for simplicity, assume it's an even integer, at least 4. Okay, so how do you do it? Well, if you take, let's assume k is bigger than 1 and take its prime factorization. And then the first step, and this is where you sort of see the two parts of the bound, something involving omega k and then some constant here. So to see where this term comes from, you take a chain of subfield subgroups. Okay, so you start off with G, and then you just choose some arbitrary prime divisor, and you drop down to this subfield subgroup. Okay, so this has got this field here, this size, has got prime index inside the field of size 2 to the k, and this gives you a maximal subgroup. And we just do the same again, and we do the same again. And so in omega k steps, so omega k here is t, the number of prime divisors. In omega k steps, we've now got down to the same group, but now defined over the field of 2 elements. Okay, so we get the bound that the depth of G is at most omega k plus the depth of SPR2. So now we just look at SPR2, and then at this point, we could irreducibly embed a symmetric group inside that group, which gives us a maximal subgroup. So we take the fully deleted permutation module over F2, that puts S2R plus 2 inside there as a maximal subgroup. And then, of course, that symmetric group has got depth at most 24, and that's where the bound comes from. And that's really where that 3 omega k plus 36 comes from in general. It's by taking an appropriate chain of subfield subgroups and then getting down to some group essentially defined over a prime field and then going a little bit deeper and landing on a symmetric group. That's sort of the idea. Okay. And if you assume that R at least 5 is odd, something very similar holds. Okay, so you get omega k plus 28. You've got to slightly tweak the argument. Okay, so let me just focus on one of the special exceptional cases. So I mentioned this 3 omega k plus 36 bound holds, but you've got to be careful in a handful of groups in characteristic 2. Here's one of them where you've got to be careful, and we can really see that this is genuinely different to the other groups we looked at. So here I'm taking PSL2, 2 to the k, and let's assume that k is an odd prime. Okay, so then by thinking about the maximal subgroups of G, it's not too hard to show that the depth of G is 2 plus this minimum here. Okay, so the minimum of the number of prime divisors of 2 to the k minus 1 and 2 to the k plus 1. Okay, so that's not too difficult to show. We know what the maximal subgroups look like. There's only the Borel subgroup and there's some dihedral subgroups, and that's really quite easy to analyze. And so this formula pops out. But now this is getting into, so you can sort of see here, there's some really sort of difficult number theoretic considerations coming into play here. I mean, how many prime divisors does 2 to the prime minus 1 have? Or 2 to the prime plus 1? So it's going to be difficult. You see, the bound that we can prove in all the other cases is of the form 3 omega k plus 36. K here is a prime number, so omega k is 1. So we'd be if this was going to be true in general, we'd be saying that the number of prime divisors of 2 to the k minus 1 or 2 to the k plus 1 is bounded by a constant, and that's not going to be true in general. In fact, it's quite difficult. It's a hard problem in number theory to sort of say how many prime divisors such a number will have. I might say a little bit more about that shortly. So you can sort of see this is genuinely different. You run into the same problem with the Suzuki groups and the unitary groups as well. Okay, so just in case you're wondering, here's the table giving you the answers of length and depth for sporadic groups. They can all be worked out. We know enough about the maximal subgroups of sporadic groups to work out all these numbers, and it's a fun problem to do so. And you can see here that the monster does come in as the sporadic with the largest length, 52. But notice things like the baby monster has got very tiny depth. Okay, so its depth is only 3 because it's got this little tiny maximal subgroup sitting inside there, which has got depth 2. So the baby monster's got depth 3. So those numbers can be computed without too much trouble. Okay, what about thinking about small length? So now let's think more generally. So if we take a non-abelian simple group, then the first observation here is that the depth is at least 3, and we saw on the previous slide it could be 3. The baby monster's 3 is an example. And if the depth's at least 3, then of course the length has to be at least 4 by Iwasawa's theorem. You know, if the length and depth are equal, the group's supersoluble. Okay, so how do you prove that? Well, that's really easy. So let me just show you. So if you have a group of depth 2, so you'd have some unrefinable chain like this. G goes down to H and then down to the trivial subgroup. Well, that H is going to have prime order because the trivial subgroup's maximal. And because H is maximal, the normalizer is either G or H. So it's either a normal subgroup or it's self-normalizing. And so in the self-normalizing case, you get a Frobenius group on the set of cosets of H. So again, in both cases, you have a non-trivial proper normal subgroup. So you can't find a simple group of depth 2. So the depth is at least 3, and the length's at least 4. Okay, so thinking about small length, so a question would be, are there any examples where the length actually hits that minimum value 4? Okay, are there any simple groups of length 4, which is the smallest it could possibly be? Okay, so it turns out here other people have thought about this question in earlier work. So there was a series of papers by Yanko and Harada in the 1960s who looked at length. This was all obviously pre-classification days. I'm not exactly sure what the motivation was for considering it, but they proved some nice results. So here's a result of Yanko from 63, which started off this sequence of papers. So he classified the simple groups of length 4. And he showed you that the examples are A5 or PSL2Ps with a bunch of number theoretic conditions. So PSL2P, P's a prime. You've got this congruence condition here. So this congruence condition here is guaranteeing you A4 was a maximal subgroup of PSL2P, which is what you're going to need. And then this condition is saying that the dihedral subgroups are not going to have length which is too large. Okay. And I've written down here the first 10 primes that satisfy all of those conditions. So it sort of looks like there's probably infinitely many such primes, but That's way beyond current sort of technology in number theory to be able to prove that. So that's not known. So it's not known if there's infinitely many. So it becomes an interesting question to ask, well, for what integer can you say there are infinitely many? What's the smallest integer so that you can, integer k, so that you can say there really are infinitely many simple groups of length at most k? So it's probably, the answer is 4. I mean, presumably there are infinitely many, but that's rather difficult. So we were thinking about this, and we got in touch with Roger Heath Brown and asked him what he knew about this. And so he actually was able to prove a theorem for us, which went as in an appendix to our paper. So we didn't really understand any of the mathematics in his proof. He used some analytic number theory and sieve techniques. But he was actually able to prove that you can find infinitely many prime numbers, so that the number of prime divisors of p plus 1 and p minus 1, both of them, is at most 8. And that seemed to be about the best that we can do, and I believe that's the best known result in terms of prime divisors of a prime plus 1 or prime minus 1. Okay, we think it should be, there's probably infinitely many with this, but 8 you can actually prove using current technology. And then now, by thinking about taking those primes and thinking about PSL2Ps, you very easily show that now there's infinitely many simple groups of length at most 9. And in fact, it's actually not very hard. I mean, we did this in the paper. We can actually determine all the simple groups of length 4, 5, 6, 7, 8, 9. It's not too difficult to do that. And we stopped at 9 because we knew at that point we'd hit infinitely many. So that wasn't too difficult. But it's sort of a nice connection with I think an interesting problem in number theory. What about depth? Okay, so one of the things we proved, so depth has to be at least 3, and there are examples. The baby monster's one of them. And it turns out we can classify all the simple groups of depth 3. And that's not maybe too surprising, because if you have an unrefinable chain of length 3, so you drop down to this maximal subgroup, that maximal subgroup in turn has to have a maximal subgroup that's cyclic of prime order, and that's rather restrictive. That puts serious restrictions on what that first maximal subgroup you drop down to looks like. In particular, it's got to be soluble, and so we know enough about soluble maximal subgroups to be able to analyze that situation, and we get a complete classification. So I won't write them all down, but I'll give you a couple of examples, and sort of interesting prime numbers crop up. So you get alternating groups of degree 2p plus 1, where p is a Sophie-Germain prime. So that just means that p and 2p plus 1 are both primes. And you've got to throw away some small cases to get depth 3. You get Suzuki groups in the presence of Mersenne primes. They come into play. So of course, it's not known if there's infinitely many of these sort of flavors of primes. And so we might be in a situation like we had for length, where it reduces to a very hard number theory problem to determine if there's infinitely many. Fortunately, here it doesn't. It's very easy to see there's infinitely many, because we just need the infinitude of prime numbers, and that's all we need. So if you take PSL2 3 to the k, and k is any odd prime, then that has L23, PSL2 3 as a maximal subgroup, and that's A4, and A4's got depth 2. So we know there's infinitely many simple groups of depth 3. Okay, so that's sort of an interesting contrast with the length situation. So on the length side, it's very hard to determine if there's infinitely many of the minimal length, but it's quite easy to describe what the simple groups of length 4, 5, 6, 7, so on actually look like. Here it's completely the reverse. So here it's not hard to see that there's infinitely many of minimal depth, but it becomes very, very hard to try and extend that result to depth 4, and it's probably not a doable problem. The issue here would be if you try and classify the simple groups of depth 4, well, you can reduce it to trying to figure out, well, what are the simple groups that contain a simple maximal subgroup of depth 3? And that's difficult. That seems a very hard problem and not probably feasible. So we can't extend this from 3 to 4, whereas length you can go from 4 to 5 to 6 and so on. Okay, so small depth. So let me say something about length versus depth. This is the sort of final slide I'll have upon finite groups, and then we'll look at some extensions of these notions to other interesting algebraic structures. Okay, so associated to thinking about length and depth, you could look at what's called the chain difference of the group. So that would be the length minus the depth. And you could also look at the chain ratio of the group, which would be the length divided by the depth. Okay, so both things have been studied in the literature. So of course, if you phrase Iwasawa's theorem in this context, then Of course, he's telling you that when the chain difference is 0, well, obviously if and only if the chain ratio is 1, and that's precisely when the group is supersoluble. Okay, so that's a way of phrasing Iwasawa. So it turns out here, if you think about simple groups, so if you take a simple group, the chain difference has to be at least 1, but there are examples when it's equal to 1. They were classified by Brewster, Ward, and Zimmerman in the early 90s. So they came up with a list of all the known examples of simple groups where the chain difference is 1. What you get is A6, and you get a bunch of PSL2Ps with some strong number theoretic conditions on the primes. And again, it's one of those situations where it's not known if there's infinitely many or not. It's a hard number theoretic problem. Okay, but there are examples where the chain difference is 1. For the chain ratio, if you take a simple group, then of course the chain ratio has to be strictly bigger than 1 because the length is strictly bigger than the depth. But there's some interesting questions you could ask sort of asymptotically. Is it bounded away from 1? And if it is bounded away from 1, can you work out, what is there a constant? Is there something you can work out? So that's a problem that we looked at. And it turns out it is bounded away from 1, and you can do it by 5/4, and that's optimal. Okay, so there are examples of simple groups where it is 5/4, but nothing smaller than that. Okay, so there are just some sort of, again, some variations in thinking about length and depth and trying to compare the two, the natural things to consider. Let me mention one final thing here. So one nice question is the following. So we know obviously that the depth of a group is bounded above by the length. But for, and we know that the two numbers can be equal. But for a simple group, an interesting question would be, is it possible to show that the depth of the group is bounded above by a constant multiplied by the log of the length? Would be an interesting question to look at. If you think about the results I mentioned before, so for alternating groups, it's clear because the depth is bounded above by a constant itself, like 20, 23. For Lie-type groups, that's where it boils down to. For Lie-type groups, if you stay away from those special cases over fields of characteristic 2, then we're basically bounding the depth by a constant times omega k. Okay, and omega k is at most log of k. That's the number of prime divisors of k. And it's pretty easy to see just by using the results that the length of a simple group of Lie-type over a field f p to the k, the length is at least k. I mean, it's at least the length of the Borel plus the rank, and the length of the Borel is at least k. So in fact, this is true as long as you stay away from those difficult cases in characteristic 2. But perhaps it's even true in those cases, but that's, again, leads to hard number theory problems. So if you go back to one of the problem cases we talked about before, so PSL2, 2 to the k, the k is at least a 3 and an odd prime, then the length is 1 plus the length of the Borel, which is this expression here. Okay, so let's think of this maybe just sort of as k. And the depth is 2 plus the minimum of, the number of prime divisors of 2 to the k minus 1 and 2 to the k plus 1. And so what you would need if this question had a positive answer for all simple groups, then you'd have to answer this extremely hard question in number theory, which is that if you take a sufficiently large prime k, then the number of prime divisors of 2 to the k minus 1 is essentially at most the log of k. And talking to number theorists, that's way beyond current estimates, even if you assume things like the generalized Riemann hypothesis and the ABC conjecture. It's way beyond what you can do with current estimates. But it's, I guess, expected to be true, but very hard to prove. Okay, so that's some sort of a survey of some of the results we've got for finite groups, in particular finite simple groups of length and depth. So with the project with Martin and Anner, we wanted to go beyond finite groups, and so thinking, well, are there natural notions of length and depth for other interesting groups, certain infinite groups, for example, maybe even other algebraic structures? So that's what I'd like to tell you about for the final 10, 15 minutes of the talk. Okay, so infinite groups. So I'm going to tell you about algebraic groups. So let's take G now to be a connected algebraic group over an algebraically closed field K of arbitrary characteristic P. So think here in terms of, like, the general linear group or the special linear group and so forth, or maybe one of the exceptional simple groups. Okay, so here, of course, these are infinite groups, and so we've got to modify our definition of an unrefinable chain. So we thought a little bit about the best way to do that. And what seems to be the best definition is the following one. So we'll take an unrefinable chain now. So it'll still be a strictly descending chain of subgroups. And because we're in an algebraic group, we'll want those subgroups to be closed subgroups. But the important condition here, so we have a maximality condition, but the important condition we're imposing here is that these subgroups are connected. Okay, so these should be maximal, so G1 should be maximal among the closed connected subgroups of G, and G2 similarly for G1 and so on. Okay, so we're going to pass down through a chain of maximal closed connected subgroups. Okay, so it's first observations with this. So we'll define length the obvious way, the maximal length, and the depth to be the minimal length, so just an analogy with situation with finite groups. And one of the first things you can observe, well, of course, the depth is at most the length. And now, of course, you can't talk about the number of prime divisors of the order of the group. It's an infinite group, but you can look at its dimension. And because we're dropping down, we're taking a chain of connected subgroups, so the level of varieties, these are irreducible varieties, and if you have a containment, a proper containment of one irreducible variety in another, the dimension is strictly less. So at every step in that chain, the dimension is dropping by at least one. So that's the equivalent of losing at least one prime divisor in the finite case. So the length is at most the dimension of the group now. Okay, so that plays the role of the number of prime divisors. Length is still additive, so that's not too hard to show. So length is still additive with respect to a connected normal subgroup N. Depth isn't, and depth is also not going to be monotonic in general, but again, we can get the same inequalities like we had before for the finite groups. Okay, so that's the setup. Let me show you an interesting example. So if you take SL2K, so special linear group over the field K, so 2 by 2 matrices, and you look at the Borel subgroup, which is just the upper triangular matrices in this group, and you take a maximal torus T, so the diagonal matrices, and you think, well, what could I've got to drop down at the first step to a maximal connected closed subgroup, so I'm going to have to drop down to the Borel subgroup. There's no choice. So you drop down to the Borel, and then inside the Borel, you could either drop down to the torus, or you could take the unipotent part as well. That would also be a closed connected maximal subgroup. So in particular here, the length and the depth are both equal, and they're both equal to the dimension of the group, which is 3. So this is already showing you that the situation with Iwasawa is slightly different here. So Iwasawa for finite groups, the condition for length to equal depth was supersoluble. Well, this is obviously an insoluble group where the length is equal to the depth. So it's a little bit different. But it turns out it's not too far away from the situation with finite groups. Okay, so that's an example. Let's get to one of our results. We proved about these things. So you take a general connected algebraic group, G, take its radical and take its unipotent radical, and take a Borel of the reductive quotient, G over the unipotent radical. Then we can prove a bunch of things. So firstly, we can show that if G is a soluble group, then the length is equal to the depth, and it's equal to the dimension of the group, in fact. Okay, so that's always true. Going the other way is quite interesting. So if the length is equal to the depth, then either the group is soluble, but of course there has to be an OR here because we have this example up top with SL2K. But what we can prove is that OR, this quotient of the group by its radical is A1, in other words, is an SL2, it's SL2K. What we can't get is what we'd really like is something going in the other way, which guarantees us that the length is equal to the depth. And unfortunately, this condition is not the right one because there are examples it's not hard to construct examples where this property is satisfied, but this one is not. It's sort of a little bit subtle, and we weren't able to pin down precisely what that condition would be essentially on the extension here to guarantee that the length equals the depth. So that still remains open. Okay. The other thing we could do was actually, which is quite nice, is actually have a general formula for the length of a connected algebraic group, independent of the characteristic. Okay, so a very nice clean formula. So you just take the dimension of the unipotent radical, you add on the dimension of this soluble Borel subgroup, and then you take the rank of this of the semi-simple part of the reductive quotient. So that's a general formula that works for all characteristics. And if you specialize to the case where G is simple, then you actually get a nice observation here that the length is equal to the dimension of the Borel, which is the same as its length because it's a soluble group, plus the rank. And that now ties in with the Solomon-Tooule theorem we saw before for finite groups, proved in characteristic 2, and then proved for odd characteristic if the exponent of the prime was large enough. Whereas here we've sort of removed, if you like, sort of like to the algebraic closure of the finite field, and things are all smoothed out, and we recover the result. And the proof of this is a lot easier, as things often tend to be in the algebraic group world than the finite result. In fact, let me just sketch out the argument because it's quite straightforward. Okay, so how does it work? Well, it goes by induction on the dimension of the group. So the base case is when you've got a connected algebraic group of dimension 1, so you're either the field or you're the multiplicative group of the field. Okay, so that's easy. It's going to be 1 in both cases. And then for the larger dimension, by using additivity of length, it's easy to reduce to the case where the group is simple. That comes out rapidly, so you can assume your group is simple. And then now what we're trying to do is look at, we consider the first maximal connected subgroup we would drop down to from G. And by the Borel-Tietz theorem, either this subgroup is parabolic or it's reductive. And so there's 2 cases to consider. That's quite straightforward. So if you take a parabolic subgroup and its Levy decomposition, and you use additivity and induction, so additivity gives us that it's the dimension, the length of Q plus the length of L. And then for L, we can use the fact that it's got smaller dimension, so we can apply the inductive hypothesis, and we see that the length of M works out to be the dimension of B plus R minus 1. Okay, we're trying to show that the length of M is always at most that number. And that's what we're trying to do. So you actually get equality if you drop down to a parabolic. And if you drop down to a reductive subgroup, then again you can apply induction. So now it's reductive, so this uniponent radical is trivial. So it's the dimension of the Borel plus the rank of its derived subgroup, and a little bit of work shows that this is at most this number, and the rank of M is at M dash is at most R minus 1. Okay, so that comes out really quite easily. So it's much easier in the algebraic group world than the finite situation to prove that result on length. Okay, what about depth? Well, again, as for finite groups, it's different, and it behaves differently, and it's sort of more complicated to study. And here it does depend significantly on the characteristic of the field. So the formula for length didn't. It's a general uniform result for all P. Here it does actually depend on P, and we can see that with examples. If you take E8, and you play around with the subgroup structure of E8, then you get this result on the depth. It moves around according to P, just because the structure of the maximal connected subgroups depends on P in a significant way. So here it goes from 4 to 9. And the idea is that the depth gets bigger as the prime gets smaller in some sense. So for example, if you're in the first case where P is 0 or large, then you can find a maximal A1 subgroup inside E8. So you can just drop straight down to that thing, and A1's got depth 3, so E8 gets depth 4 in that situation. So it's easy. For small primes, you don't have such an A1 subgroup, so you have to sort of dig deeper, and it's going to take you longer to get down to the trivial subgroup. And in fact, sort of trying to figure out, so it's quite a fun exercise to try and figure out what the fastest way to get down to the trivial subgroup is. And often there's more than one choice of how to do it, so it's not necessarily unique. So here it turns out if you go by this D8 subgroup and you take this big chain, and here you have some sort of like diagonally embedded subgroups and so on, you get a chain of length 9, and you prove that that can't be beaten. So the depth of E8 when P is 2 is 9. Okay, so it does depend on P. So what we could prove here is the following. So for depth, so if you're in characteristic 0, then we can do everything. Okay, so in characteristic 0, we can work out the depth of exactly of all of the simple algebraic groups, and it turns out that it's at most 6 in all cases, and A6 is the exceptional case. SL7, it turns out, actually reaches that bound. If you're an exceptional group in positive characteristic, then again we have a complete answer for all the exceptional groups in all characteristics. And the example I had up on the previous slide of E8 in characteristic 2, that's the case which gives you the largest depth of 9. That's the only one. But the interesting case here where there's more work to be done perhaps is the case in positive characteristic and a classical group. Here we don't have a formula for the depth. We don't know the depth in general. Again, by sort of exhibiting an appropriate chain, we can show that the depth is at most that number, which depends on the log of the rank. But we don't have, again, it's a bit like the finite group situation. We'd like to put something on the other side, but it's difficult to generate lower bounds on the depth. But what we can show is that the depth does behave very differently in positive characteristic than it does in characteristic 0. So let me remind you, so in characteristic 0, the depth is at most 6. But in positive characteristic, if you take a classical group, the depth goes to infinity with the rank. So we could prove that. We can show that the depth goes to infinity, but we couldn't. This is not necessarily the right expression for how fast it's tending to infinity. And of course, these proofs rely heavily on the work of many decades of people like Dinkin, Liebeck, Seitz, Testerman, who've the detailed studies of the subgroup structure of the simple algebraic groups. So that's what we rely on. Okay, so that's the sort of situation with algebraic groups. I'll just mention very briefly now just two things to finish. So we also looked at Lie groups, so you can sort of see that there's an industry here, there's other different types of groups we could look at. So we looked at Lie groups, and we took the easy case of compact Lie groups, and Martin's student, Damien Sercombe, took the hard case of the non-compact Lie groups. So we did the easy work. So if you take a compact connected Lie group, then again you can define unrefinable chains in exactly the same way as we did before, going to maximal closed connected subgroups. And here the situation, if you take a compact connected Lie group, then the situation is very similar really to the corresponding algebraic group over the complex numbers, essentially. And we know everything that's going on in characteristic 0. So here I've just tabled up the results for simple compact Lie groups. Okay, so we have the length. Okay, here you go, that's what it looks like. We work them all out. And we can work out the depth precisely in all cases, and it ranges between 2 and 5. What's quite nice here for compact connected Lie groups is that we can actually have a precise Iwasawa analog for when the length is equal to the depth, which was lacking for the algebraic groups. We can do it here. It turns out that it's equal if and only if it's a torus or the derived subgroup is SU2, okay, in this situation. So it turns out to be a little bit easier to analyze. Okay, so that's for the compact Lie groups. And then just to finish, let me report on some very, very recent work due to Damien Sercombe, who's one of Martin's recent PhD students, and Anna Shalev. So they've tried to extend things beyond groups. So Martin sort of invited me to give this talk on Wednesday, so I wrote to Anna and said, I'd like to add a couple of slides on at the end here, if you can send me a report on like what the latest is on this project. It's not on the archive yet, so I've got Anna's permission to tell you about what they've been doing, and hopefully I'll sort of report the results accurately. I think it's still very much a work in progress, but they've got some really interesting ideas. Okay, so they look at algebras. So take a finite dimensional associative algebra over a field K. You look at length and depth here as well. I mean, there's a natural notion of unrefinable chain, where you would now drop down to a maximal subalgebra at each step. Okay, so that's what they look at. So you can ask, well, yeah, what can we say in this situation? So here it's sort of interesting because there's going to be certainly a dependence on the field K is going to enter the picture in a significant way. So let me just mention a couple of things they've done. So firstly, they show that length is additive with respect to ideals. So it seems to be a good definition. If you say take a matrix algebra, so the length of a matrix algebra, then it's not too hard to show that it's, again, you can sort of take a chain of sort of parabolic subalgebras down to the upper triangular matrices, and then you've got the length of the diagonal matrices and then the length of the strictly upper triangular matrices, and this is all quite easy to, this is not too difficult to work out when you get this expression over here. For the length of a matrix algebra over the field K, if you take a division algebra over K, because of course that's going to be interesting for the general case, they also have a sort of an analogous expression where now it's basically the same, but now you've got to add in the length of the division algebra over K, and you've also got to add the degree of the division algebra over K in as well, but otherwise it's the same. So you recover this if you take K to be D. So that's nice. So they've got some nice results there, and they've got a load of other results. Another thing they show is that if it's a nilpotent algebra, then the length is equal to the depth, it's equal to the dimension. Okay. So since length is additive with respect to ideals, and since for the nilpotent case it's equal to the dimension, they get a general formula for the length of a finite dimensional algebra, and it's given by this expression here. So if you quotient out by the Jacobson radical, then you can express that quotient as a product of matrix algebras over division, over division algebras over K, so like this, and then basically now just use additivity and the fact that the length of the Jacobson radical, it's a nilpotent subalgebra, so it's equal to its dimension. So there's a nice formula for the length. For the depth, it's more difficult, as it is for groups and it is for the algebraic groups and so on. It's a little bit more difficult, but they can show, for example, that the depth of a simple algebra, so one of these matrix algebras over a division ring, you can bound it above by this term, 6 times log n plus the depth of D. And in fact, if you're over an algebraically closed field, then they also can come on the other side here, which is quite interesting. So they can show that this is essentially the right answer. So here, you bound it above, so the depth of K is just 1, but over the other side for a lower bound, you can get it 3 log n plus 1, which is quite nice. And it may be possible to sharpen that. I think they're working on trying to maybe shrink their gap there a little bit, but that's a nice result. And also they've got a result, again, sort of an Iwasawa analog for algebraically closed fields, and you have other more complicated statements for more general fields, but they can determine when the length is equal to the depth, and that would be precisely when you look at the quotient by the Jacobson radical, and you get these matrix algebras here, and you should only see matrix algebras of dimension 1 or 2, nothing larger than that, and that will get you length equal to depth. Okay, so I think that's a good place to pause. Thank you.
Well, these are actually comments rather than questions, if I may. First of all, you mentioned that question, can you find the length of the symmetric group without using the classification of finite groups? Back in the early 80s, when I was doing that, we had Bobo's elementary bound, which, as you know, is sub-exponential, whereas the lower bound that you would need to get a longer chain is exponential. And if you just put those two together, it's true for n greater than or equal to about 1,000.
Oh, right.
So you will only have to deal with symmetric groups of 3 up to about 1,000.
Okay. Okay, so perhaps an exercise for a PhD student.
No, I mean, I never actually had the courage to sit down
I see.
and do it.
I see.
This is one of those things that really, really should be possible to do it without.
Oh, that's interesting. Okay.
The other is lengths of other kinds of things. James Mitchell and Jan Persson, I have a paper on lengths of semigroups.
Oh.
Very, very different because you don't have the ground distance. So the length can be as large as the order of the semigroup.
I see.
And we have an exact formula for inverse semigroups in terms of groups. If you knew the lengths of all groups, this formula would give the length of all inverse semigroups. And we have bounds in some other cases.
I see. That's interesting. So is there a preprint on that? Or?
Oh, we published it a few years ago, I think in the Israel journal.
Oh, right. Okay. Okay.
I can send you a copy.
Please do.